Yeah, so I'm happy that my talk follows great talks by Anislady and Alejandro about continuing about neural mass models. And this is more a technical methodological talk about how we can improve efficiency of running these simulations, because these are painstakingly difficult to do these simulations. And I'm going to suggest that using GPUs would be a solution to that and show you a toolbox that does that. Okay, so so a lot of these concepts that I'm going to talk about in the first few slides were covered in the great talks today and in the past days. But basically, so first of all, why would we be interested in doing brain simulations? Generally, it allows us to ask questions that are not possible to ask otherwise. You cannot see in the data. So for example, you can ask questions about hidden features in the data, or it provides you with a platform, an in silico platform in which you can manipulate the model, you can stimulate it, and then see how it behaves. These are not possible in vitro or in vivo, generally. And then the general framework of how this is done, conceptual framework of how this is done at different levels, is that we first start with doing some simplifications, doing some abstractions of the phenomenon or the component that we are studying. It could be a neuron, it could be a brain region or a whole brain, and describe its activity or dynamics by some mathematical equations. These are usually a system of differential equations, which, for example, describe how firing rate, how synaptic gating variable, etc., vary as a function of time and other inputs, etc. But then the solution to this system of differential equations is generally usually not a closed form solution, so you cannot derive that analytically, and instead what you should do is to run computer simulations, which means that you start with some states and then just follow it time after time point until you get to the last time point. And then eventually you would want your simulation to look like the data that you are you're studying, so the actual data that you have measured. So then you would then do a comparison of the simulated data with the actual data. And based on this, if it's not a good fit, then you go return to your model, adjust its parameters, tune it, and do this process over and over until you get to a good enough simulation which you can then study. Okay, so as Anislady mentioned, there are different levels of doing these models. I mean, you can simulate individual like synapses, neurons, brains, etc. Right? I'm now going to focus on simulating the whole brain using neural mass models. And this approach, basically, we simulate each node of the brain as a neuronal mass, for example, or a few neural masses, and then let these nodes to be connected to each other based on a structured connectome. So let's just dive in to the actual methodology of how this happens. So suppose that you want to model a particular subject or create a digital twin for that subject, if you will. And then you put that subject in a scanner, get a resting state fMRI. It would look like this, for example. Like this is an example there. And then you want to create a model that can create the data or simulation that looks like this in some features. So then you would then decide on the nodes of the brain that you're simulating. So you just select the parcellation, right? So for example, here I'm just showing a few nodes. Then we would connect these nodes to each other based on a structured connectome. This can be from the same subject that you were simulating, or it could be a template structured connectome from another source. And then we then define what happens inside each node, and then there are a lot of established models out there, neural masses, that would describe how the dynamics of this each node should be defined. What are the mathematical equations that would describe the dynamic activity of each of these nodes? And I'm here showing you two examples. Reduced Wang-Wang model and further reduced Wang-Wang model. So I'm going to focus more on the model on the left, in which each node is modeled as neural masses, excitatory and inhibitory. These are connected to each other within the same node, and they are also connected between nodes. And then the connectivity is controlled by some parameters, which you can see like these small letters. And these parameters are what we can control and tune to make our simulation look better or look more similar to the observed. So suppose that you start with some parameters, some random parameters, and then you run a simulation. And actually, this is the optimal simulation. So you run a simulation, and it looks like this, right? But then you would compare your observed data, racing is at fMRI, with simulated racing is fMRI. And the comparison happens, for example, by comparing the function connectivity patterns. And then we then adjust our model. We had these parameters, we can tune them, go up and down, and so on. And then simulate again and do the comparison again and do this process iteratively over and over and over until we find a good simulation. Now, as I mentioned, there is a methodological challenge in that, especially if your model is complex, and especially if you're doing individualized modeling, meaning that you're creating different models per subject, then you will end up running a lot of simulations, thousands to tens of thousands of simulations per subject, and you usually have to do these in different runs, and then if you have 1,000 subjects, then it can quickly explode, right? And then each of these simulations also, as I mentioned, involves a lot of calculations. You go through millions of time points and a lot of nodes. And just a fun fact, I mean, so Hodgkin and Huxley, you probably know their model. They did this with a mechanical calculator, but now we have computers to let us do that. It is nice, but still, our computers struggle with this because, again, you have to do a lot of simulations and they take time. Now I'm going to argue that using GPUs might be a solution. So this is a nice presentation of what's the difference between CPU and GPU. Generally, CPUs are designed for serial processing. So you have one thing or several things that can do one thing at a time, right? But they can do this very fast and very, very nicely. But then you have, on the other hand, on the right side, you have GPUs, which are from the get-go, from the beginning, were designed for doing parallel processing. Because, I mean, no, never mind. I should not get into that. But anyway, so GPUs are designed for parallel processing, whereas CPUs are designed for serial processing. Now we can apply this to simulations of neural mass models. Generally, so there are a dozen great tools out there which allow you to run these simulations of neural mass models. And most of them are implemented on the CPUs. So on CPUs, what happens is that you can do one thing at a time. So what happens is that the CPU does calculations of one simulation, one node, and one time point at a time. And this would obviously take time, right? I mean, of course, you can have multiple CPUs and then connect them together and then parallelize simulations, but still, it's going to take some time. But on GPU, because of how it is designed, how it works, it's possible to do parallelization across both simulations and nodes at the same time. And this should make it faster. And that was what we expected. And I'm going to show you that it actually does. So this is a little bit complicated graph, but maybe it's the most important graph in my presentation. So here I'm showing you the code that we have implemented. We are running 60-second simulations, right, for 100 nodes. And we are running different numbers of identical simulations. So we start with 1, and then you see this logarithmic scale would go up to 131,000. And look at the last time point, sorry, not time point, the last point that we can do, never mind, I mean, you know, that's the last one. 131,000 simulations, right? And I want you to compare the black line and the red line. The red line shows you an A100 GPU, which takes only 19 minutes to do 131,000 simulations. But on a single thread of CPU, it would take 15 days to do this. So 19 minutes versus 15 days. And I can do this more formally. Look at the speed up of compare the gain that we get from using GPUs. And you can see on the right that maximally, like when you do 131,000, GPU is 1,370 times faster than CPU, which is super cool, right? And this is only just for 100 nodes. There is another complication of doing parallelization on simulations on GPU. So I said that we can do parallelization across simulations and nodes. And doing parallelization across nodes has a very nice implication. One, look at the first time point, look here. You can see that that even doing one simulation is faster on GPU, right? Because we are also doing node parallelization. But it has another nice implication in that when you increase the number of nodes on CPU, so these neural mass models, as I mentioned, they have to keep track of all the connections, right? In a structured connectome, and a structured connectome is a matrix. So as you increase n number of nodes, the size of the matrix increases quadratically. And therefore, if you're doing the CPU implementation, then the compute time also increases quadratically, as you see in this gray map. But on GPU, this doesn't happen. The increase is linear, which is super nice. And if I did the previous slide with 500 nodes, we could have observed even higher than 1,300 times faster performance on GPU. Okay, yeah, but then so far I've been focusing on scaling this like GPU implementation to higher number of simulations. But another level of scaling is to scale it to higher number of nodes. At the moment, the toolbox only supports up to 500 nodes. But during discussions that I had with colleagues in this nice workshop, I've also started working on different implementations of scaling the number of nodes up to 12,000 or so that it would enable like very large simulations, but then the number of simulations would decrease. Anyway, so all of this is included in a Python toolbox called cuBNM. BNM short for Biophysical Network Modeling. Cu is starting word of CUDA, which is the programming language used here. The core of the toolbox is written in CUDA and C++, so it's for efficiency, but in interface it's Python, so that's easier to use. And we also have Docker containers, so you can use it with Docker and Singularity. And by the way, while it is focused on GPU, it also works with CPUs. Okay, so now we have this, right? So how can we use it? We can use it to optimize model parameters of biophysical network models. And how does that work is that there are two optimization approaches included, bundled in the toolbox. One is grid search, and the other is evolutionary optimization. Grid search, what it does, as the name implies, is that it searches for all the parameters or combinations of parameters in your search space. And you do, like, for example, here I show an example of 10 by 10 grid. You will have to do 100 simulations to get to this thing. And then you look at the optimal point. But then there is another way of doing this, which is evolutionary optimization. This is usually better for high dimensional, because as you increase the number of dimensions, imagine that the grid can explode, right? Even GPUs cannot do like a 5D, 6D, 7D model. And then we could use evolutionary optimization, which would evolve in different generations towards a high optimal point. As you can see in this example, that the points generation by generation are getting concentrated around that area of higher fit. And I'm showing you, oh yeah, sorry, I forgot about this. So then within the optimal simulation or any of the simulations that the toolbox runs, you can also look inside the simulation, look at the time series of the state variables, look at the time series of fold. You can also look at the simulated functional connectivity and functional connectivity dynamics and do a bunch of different things. And here is the code of running these two. I'm not going to go through the code, but I just wanted to show you that I've tried to make the interface rather easy to use. So you could use it in two ways. One is using it as a Python, using the Python API, import it as a Python module and use it at the top. And at the bottom, you can see that you can also, if Python is not your language of choice, you can also use a command line interface. And this command line interface is also the entry point of the Docker containers. And in the middle, I hope, maybe these are too small, but I have links to Kaggle notebooks showing you demos of how these two optimization approaches work. And Kaggle is like Google Colab or Jupyter, but it's nice that it has 35 GPU hours per user per week, which is nice. Yeah, just give it a try. And these links are also in the documentations, which I will show later. So have a look there as well. Yeah. Okay. Okay. Now, the nice thing about this that we now can run a lot of simulations, right? Then this allows us to do scaling in different dimensions. And one dimension is that we can run more simulations, meaning that we can have more complex models. And therefore, like, we also here talks about that we need more complex models, right? More complex models would have more parameters, and we would need more simulations to do that. And then one way of adding complexity or adding biological reality to the model is that we could. So normally in the older papers using this approach, the assumption was that the regional parameters of, for example, connectivity between nodes, between neurons within the same node, that is homogeneous across the entire brain. But that's likely not a very good assumption. And a better assumption may be that they can be variable across the brain, and they can be heterogeneous. And there are a bunch of studies showing that if you introduce heterogeneity in the model, then it would increase the fit of simulations to the empirical data. There is one by Demirtas in 2019, and there is another one by Gustavo Deco, 2021, showing the same thing, that if you use maps to introduce heterogeneity in these local parameters, then you would increase the fit. And that is also included out of the box or in the toolbox, so you can just add 2 lines of code to the API. You just say that I want these parameters, like WE and WEI, to be heterogeneous, and I want them to be heterogeneous based on this map or this set of maps. And then the free parameters would be then the coefficients of these maps. But then the toolbox will automatically add these as free parameters, and then the problem also becomes high dimensional. And then with large number of simulations, you can fit these difficult problems, difficult optimization problems. This is just a code showing like what Demirtas et al. Did. They just used a myelin map to do this, to introduce heterogeneity. And I'm showing you the code to do exactly that. Okay, so I want to show you an example, which was my presentation last year, or the project that I did last year, was that we used this same code for scaling neural mass models to a large number of subjects using a rather complex model based on 6 heterogeneity maps. And we ran 30,000 simulations per subject, and we had 1,000 or so subjects. And our goal was to study how EI balance changes through development in adolescence. And I'm not going to go into the details of that, but then eventually we found that there is a consistent pattern of age-related increase of inhibition in association areas in both data sets. But then in this project, we actually use this code that I'm presenting here. Another example is that, okay, so we are in the BigBrain Workshop. Okay, sorry, I'm done. So how can we integrate this framework with BigBrain data? And a very, very, very superficial way of doing this is just to use BigBrain maps to introduce heterogeneity in the model parameters. So I'm just showing you here comparison of 3 cases that we do not have any heterogeneity, or we introduce heterogeneity based on Casey's MPC maps or based on Conrad's layer maps. And we can see that the goodness of fit of the 2 latter cases is higher because it's heterogeneous. I mean, it could be because of the higher number of parameters, and further tests need to be done to make sure that this is specific to these maps. But anyway, and then within the highest optimum one with laminar thickness maps, we can also then look at what is now these optimal maps of the regional parameters. So I'm basically done, but I have 2 main conclusions. One is that, use our toolbox, it's nice. The other one is that, I mean, even if you don't do neural mass modeling, I wanted to make this point that I find that GPUs are great tools for optimizing the processes that we run, the different types of analyses that we do. And a lot of times they consist of repetitions that are parallelizable, and then we have these GPUs available that can be used, that we can use. And yeah, and then now it's also like easier to program them using tools such as Namba, CUDA, or CuPy. And this is just links to the documentation in the GitHub. Just wanted to mention a few things. I'm sorry, I know over time. First of all, like this is under development, right? So if you want to contribute, if you want to add models, let me know. We can add new models as well. And also, if you face any issues, just post an issue or in the GitHub or send me an email. And that's it. Thank you very much.